go ahead and get started. It's my pleasure today to introduce one of our CITA National Fellows, Robert Andrassy, who's currently at the University of Victoria. He did his PhD at the Max Planck Institute for Astrophysique in Dashing with Hank Sprout, and then this is his first postdoc at Victoria. So if any of you are interested in dinner, just let me know after the talk. And he's going to tell us today about convection in stars.
Thank you. So as Ian said, I just started my postdoc at UVic. I also did a PhD on stellar convection, but this is not what I'm going to talk about today. I will just briefly mention my PhD work, but if any of you want to talk about that, I'll be happy to meet with you. So I know that there are not too many people doing stars in this room, probably. So I would just start with some brief overview. Convection is really important for stars because it's present essentially everywhere. Every star has some convective layers. If we are on the main sequence, then at the very lowest masses, the whole stars are convective. Then if we go to solar-type stars, we have convective envelopes and radiative cores. And if we go to slightly higher masses, then the cores of these stars start to be convective, and the envelopes are then radiative. If we go to later evolutionary stages, for example, if we take a really heavy star, like 25 or 50 solar masses, then we get these shells, and some of them are convective. This is a picture just before the explosion. And of course, it depends on the convection physics, how these convection zones spread and interact, and they can influence the structure of the supernova progenitor. And also, depending on how they merge, this changes the nucleosynthesis pattern and yields of the supernova. The complicated thing with convection is that it's actually a very fast process. It's three-dimensional, but if we just take the sun, we know that it lives for about 10 to 10 years, and the overturning time in the solar convection zone is about a month. That means that we get about 10 to the 11 overturns over the lifetime of the sun, which is way too many to do any three-dimensional simulations, because very subtle effects may be important on long time scales. So if we want to do stellar evolution, we have to stay in 1D. There's no question about that. So how to model convection in 1D? We have a theory called the mixing length theory, which is actually based on order of magnitude, really crude estimates. But the basic picture is that we have some stratification which is unstable to convection, and then we picture a blob, actually a big blob of some material, which starts rising and covers some distance, which is called the mixing length. And after having traveled for this distance, it exchanges its heat content with the surroundings and gets dispersed. Based on that picture, you can derive some equations for the convective flux due to this blob, or due to a series of such blobs, and also for the typical convective velocity. If you have convective velocity, you have a length scale, you can construct the diffusion coefficient, which could somehow approximate mixing due to convection. In this way, you multiply the velocity times this mixing length. So velocity scale times the length scale is a diffusion coefficient. This is what is usually done in stellar evolution codes if you really want to follow mixing due to convection. The problem with the MLT is that it is a local theory. So if we go to one point, take the stratification from the stellar model, based on the quantities of this, at this point, it will tell you the convective speed and thermal flux and everything. But we know that, for example, this point is influenced by blobs which started here. Convection is non-local, so this theory cannot provide the correct answer. So because of that, once we are in the convection zone, we get non-zero velocities. But as soon as we go a bit past the boundary, then the convective velocity drops to 0. There is no mixing across the boundary in this theory. But we know that first, nature doesn't like discontinuities. And second, we also have observational evidence that there is some mixing across convective boundaries. And here I just want to briefly summarize some of the evidence for it. I give some references here if you want to just check the literature and where to, you know where to start. We know that low mass stars have these deep convective envelopes, but they are not deep enough. For example, the sun, the solar convection is not deep enough for convection to reach the lithium burning layer. So the lithium abundance should stay constant over the lifetime of the sun, or at least on the main sequence. But we know that there is strong lithium depletion observed in the sun, and some low mass stars also have beryllium depletion. So there is some extra mixing at the bottom of such convective envelopes. Then it turns out that if you take a color magnitude diagram of an open cluster and you want to fit it by stellar isochrones produced by an evolution code, then you have to include some additional mixing at convective boundaries if you want to get the right shape. Otherwise, you don't fit it. In a similar way, if you take observations of double-line eclipsing binaries where you have a lot of information about both of the components, you can place them on a Hertzsprung-Russell diagram. And of course, you would want to fit both components with stellar evolution tracks at the same age, because this should be the age of the system. If you want to do that, you'll only be successful if you have included some additional mixing at convective boundaries. Again, something similar comes from astroseismology. This is really recent work of Connie Ards. She observed some OB stars and tried to fit the positional frequencies of these stars. And it turns out that, again, the observations can only be fit by the structure coming from an evolution code if you artificially increase the size of the core of these stars. So this is one kind of evidence. Then we have something totally different, novae. If we take a nova explosion, which is we have a white dwarf, it accretes some hydrogen-rich gas from a companion, and after some time, this hydrogen explodes. Of course, there will be some nucleosynthesis products from this hydrogen burning in the ejecta, but what is observed is that there is a lot of heavy metal enrichment in this gas up to metallicities of 0.3 or so. So there must have been some mixing between the white dwarf material and the accreted hydrogen. So there is some mixing. And the last thing that I want to mention is not that much of a direct evidence for convective boundary mixing, but this is relevant to the rest of the talk. It turns out that if you take models of massive stars, then they don't produce enough potassium and scandium, so that if you take these models and put their yields to a galactic chemical evolution model, then you get curves like this. Here's a function of metallicity, is the abundance of potassium and scandium. The dots are observational data, and if you take just the default run of a stellar code, you get something like this. So these curves are too low. But it turns out that if convective shells, the carbon shell merges with the oxygen shell at some point in the evolution of the star, then interesting nucleosynthesis happens, and exactly these two things are produced. And these two plots are from a paper being prepared by Christian Ritter, a PhD student in our group, and he tried to take the yields from such mergers and artificially add them to his models, and it really brings the curves up so you get a better fit. So maybe this is what happens in massive stars. So we know that there is some mixing, but what is the physics of this mixing? We have this general term called convective boundary mixing. You may know it as overshooting, but that describes a series of physical phenomena. We have things like ballistic overshooting, which is just that something is flying, some convective element is flying towards the boundary and it hits it. This boundary is stable, but it has some kinetic energy or some inertia, so it can travel some more distance. This is very difficult to achieve in stars because the boundaries are very stiff, so the typical distance traveled is very small. Then you have shear instabilities because there are flows sliding along the convective boundary, so at some point it may be unstable to shear. Then there is an effect called convective penetration, which I don't want to go into details. It's just if you have fast enough mixing, you can mix entropy, and that could produce an advance of the convection boundary on a somewhat longer time scale, longer than dynamical. Of course, every time you hit a convective boundary or a stable stratification, you get internal waves. Under some conditions, they could produce some weak mixing. And then there are two processes that I worked on during my PhD, is convective settling and differential heating. I'll just give you the brief idea. Convective settling is something for low mass stars. These have these deep envelopes, and we see lithium depletion in these stars. So the idea is that what if you take some material from the photosphere, which has very low entropy because it has just cooled off, it has released its heat, and this material is rapidly sinking into the convection zone. If a very small part of that material, like 10 to the minus 7 of it, survives almost adiabatically to the bottom of the convection zone, then it will still be very heavy. Its buoyancy will be very low, and it will just sink below the convection zone, providing some mixing between the lithium burning and the convection zone. You can have a look at these papers, or we can discuss it later. And differential heating is the idea that if you have the convection zone, it produces some temperature fluctuations, some large-scale temperature fluctuations at the convective boundary, and these propagate via diffusion into the stable stratification, which sets off a flow in the stable stratification. So this is just a theoretical idea. So there are a lot of processes, but what is actually done in practice is if you do a stellar evolution calculation, you either take some distance, like coefficient alpha times the pressure scale height, and you mix that layer on top of the convection zone with the convection zone. For example, 0.2 pressure scale heights. Or a different parameterization, which is used, is that you apply some diffusion beyond the boundary, which starts at some value, a diffusion coefficient derived by the mixing line theory, and then it falls off exponentially with some coefficient here, some fraction of the pressure scale height here. And again, we don't know what this coefficient is from first principles.
There's one additional process, actually.
They may be more.
If the boundary is supporting an active dynamo, and this is especially relevant for very luminous of all the stars, let's say typically RGB or AGB, then magnetic fields wound up below the boundary because there's some imposed differential rotation from the convection zone into the radiator zone, will themselves induce mixing due to the attempted radiation to smooth out the entropy below the boundary.
Yeah, well, this another option. But of course, there are also theories that magnetic fields actually stops mixing because of the tension in magnetic field lines. Who knows? There have been other models. This list is definitely not complete.
Well, how many of these have been directly simulated using radiation transfer plus hybrid?
Well, most of these things are really for deep interiors, so radiation transport is just diffusion. So you can simulate shear instabilities because you can simulate anything that's dynamical. So shear instabilities, ballistic overshoot. This process is slow, so you don't have enough time in your simulation. Internal waves can be seen, but the trouble there is that you need a lot of resolution at the boundary because they are almost horizontal. Convective settling is completely impossible at the moment to simulate because it's about very small things. Differential heating, you can simulate to some extent. I did some simulations in 2D, but again, it's not clear what the interaction of this with convection would be, and so on. So you can simulate some of them, but some clearly not.
Is the process referred to as dredge up related to this too?
Well, I think that what we call dredge up is something more general. It's just that convection extends in mass as the star evolves, but that includes the change in the size of the convection zone due to changing opacities, luminosity, and everything else.
So it's not actually related to the boundary.
I wouldn't call it boundary mixing. Yes, so the idea here is that we have several processes that there are various analytical theories of these processes, but of course each one of them has some parameters, and we don't know these parameters. So for example, this FCMB here in the diffusion prescription is important, as shown in these two Kippenhahn diagrams. So for those of you who don't know what a Kippenhahn diagram is, this is the structure of the star, so it's mass instead of radius, and this is some time scale, and this is the innermost part of the 25 solar mass star beyond core carbon burning. This from a work from Austin Davis, a graduate student in our group, and now these two models are identical to the left of the dotted line. They use this F factor. But Austin kept the same factor here, but increased it here. And these gray zones are convection zones. Blue is energy generation rate. You see that these carbon convection zones just look different. They are in different mass ranges, and they occur at different times and so on. So the mixing is different. And also, if you calculate some compactness parameter, it is not the same thing as what people usually call the compactness parameter. That is the same expression evaluated at core collapse. These models have been only taken to the end of the first O shell or so, but these values are different. So the structure of the star is different depending on what you choose for convective boundary mixing. Sorry?
Those were done with Mesa.
Oh, with Mesa, yes. These were Mesa models. So the question here is what we can actually use 3D simulations for. If you want to do something in 3D, you first need to pick the right convection zone. As I said, Sun does 10 to the 11 overturns in its lifetime, and the stratification in that convection zone is extreme. So we don't want to do this. If you go to an oxygen shell, it can only do 10 to the 3 or 10 to the 4 overturns, because after that, the star just blows up. So there's not enough time. And also the stratification is much weaker, so it's easier. Still, we can only do a few tenths of overturns in 3D. So we somehow have to extract the mixing seen in the 3D simulation and put it back to 1D, and carry the simulation over for some longer time, and perhaps do another 3D simulation, who knows, to recalibrate some one-dimensional model. The question is how to reduce this complicated stuff back to 1D. And also how often we have to do this during the evolution of the star. So what we would want to do is to take a complicated 3D simulation and derive an expression for the local mixing rate depending on the radius, luminosity of this shell, the stiffness of the convective boundary, and perhaps something else. So now I'd like to report on such effort in our group. This has been led by Sam Jones. And you can also see Falk Herwig, who leads our group, and Paul Woodward, which is our external collaborator. So the idea here is to do some simulations of oxygen shell burning in idealized physics. So just to get the basic parameter dependencies and to see what it looks like. We are about to submit this paper. So if you take a Mesa model, then the O shell in a 25 solar mass, solar metallicity star will look like this. So there's some time towards that's left to explosion. And here you have the oxygen shell, this core oxygen burning. if you use the same time scale, you can see that the mean molecule weight in this convection zone increases with time as the burning proceeds. And it's got two boundaries, the bottom boundary and the top boundary. And you can see that for most of its evolution, the size of the convection zone is about the same. And also the luminosity, although it has various spikes in it, it's about the same. So this should be an easy case. Now we tried to set up something similar in Paul Woodward's code BPM Star, which is based on the BPM advection method. These simulations are the star in the box type. So take the whole convection zone and put it into a box so we can see everything in all directions, 4 pi, so there is no wedge or other cutoff from the convection zone. It's simplified in the sense that we only have 2 fluids. One is in the convection zone and below it at the beginning, and the other is some lighter fluid on top of the convection zone. Their mean molecule weights are similar to what is actually in the stellar model. We can run this at resolutions of 768 cubed and 1536 cubed, but there is a very accurate PPB scheme for the transport of species, which has an effective resolution about 2 times this value. So we can resolve things like 6 kilometers. Piecewise parabolic Boltzmann. You can ask me about details later. I would be happy to tell you how it works.
More complicated than just advecting a scalar?
It does advect the scalar, but in a very complicated way.
It's pretty standard.
Yeah, so here I just want to show how similar our model is to the star, although we didn't try to do a precise fit or something like that. Physics is really one of ideal gas, no radiation, and so on. So these lower curves here, the total pressure in BPM star, the gas pressure here, this dashed line, and some contribution from radiation pressure and pressure of degenerate electrons. We only have one gas pressure, there is no radiation pressure, but the total pressure is fit pretty well. This is as a function of mass here. If we go to the density plot, then this is the density in ppm star, so it's about 10 to the 6 gram per centimeter cubed, and this is in Mesa. This step is the beginning of the carbon convective shell, which we don't model. This is why it's not present here. We only have stable stratification there, because this carbon zone is very big. It wouldn't fit to our simulation box. Energy generation is also approximate. If you look into ppm star, then you have some nuclear energy generation rate, which peaks here at the bottom of the oxygen shell, which is mostly oxygen burning. You see several orders of magnitude in the energy generation rate here. And then you have the carbon shell. There's quite a large contribution of neutrino losses. So this is an advanced evolutionary state. So plasma is losing neutrinos like crazy. So we don't model these things exactly. We just replace this minus neutrinos by an effective heating source, which is this gray curve here. And we can tune the luminosity of this source to, for example, see how the properties of the simulation change when you change the luminosity that drives the convection. Yeah, so let's have a look at some movies. This first movie, where is it? It's here. So, this first movie will show you a slice through the simulation box, and it will be shown in terms of vorticity, so the curl of velocity. This shows you all structures in the turbulent flow. So at the beginning there is no vorticity. Convection still has to develop. I ran it for some time, And this is the first thing that happens. You see a clear cross symmetry. This is because the convective instability just starts, and this whole thing is in a box. It's an Euclidean geometry. So any slight imbalance in acceleration terms will be shown by some symmetry in the flow field, but that disappears quickly after convection starts. And then you get this. So the convection zone is here. This is its bottom. You can see some internal waves here. And later you'll also see some internal waves here. This movie will change the color scale soon. But you see there's a lot of structure in this turbulent field. So the simulation is really, really well resolved. This is a 1536 cubed. There are even some structures which cannot be seen in this movie. You need more resolution to only show them. So it does this, and now it should change the color scale. So you can also see some waves here at the top. So this is what vorticity looks like. Now let's go to the second most important thing. Oh, well, this is actually more important than vorticity. And this encodes on the color scale the fraction of volume of the fluid from the top. So this is the top of the convection zone, and this red thing means that all of this fluid here is the lighter fluid that we first placed on top of the convection zone. Then there is a transition layer, a thin one, where you change from one fluid to the other. As convection starts, it can entrain some of this fluid at very small levels into the convection zone. And we are, of course, interested in how much it can bring into convection zone, at what rate. So this is what happens. Convection is just starting, but you can already see some gradients here and various plumes, and the whole convection zones is getting brighter and brighter and brighter. That means that there is more and more of this stuff in the convection zone. But also here you can see the effect of the PPB transport scheme. It's got so much resolution that you really need a big screen to look at the simulation.
So sorry, what's the scale of the diffraction in terms of?
Yeah, I should have said this. I don't remember what the full scale is, or let's look at this picture. But so red is 1. That means this fluid is fully fluid 1, let's say. And these levels here are like 10 to minus 4 to 10 to minus 3 at most. So it's a small fraction. So let's go back to this presentation. And now, one of the things that you may have noticed is that this boundary is not a boundary condition. There is still a stable zone on top of it, but this boundary remained during the whole movie almost perfectly circular. So this boundary is quite stiff. How stiff? You know that every time we run such a simulation, we have to apply some smoothing so that the boundary is resolved. This is the boundary stiffness in terms of the buoyancy frequency n squared as a function of radius. The convection zone is here, and the boundary we are interested in is this one. This thin gray line comes from Mesa, and the other lines come from BPM Star. So we get very similar gradients and also absolute values of n squared. So we have about the right stiffness at this boundary. And now we want to analyze this boundary. And this is a big difference from star evolution calculations, because in star evolution you have a well-defined position defined by the Schwarzschild criterion. Here the convection zone stops, then you have no convection. But if you look at the simulation, that doesn't help you. In terms of the Schwarzschild criterion, half of our convection zone would be slightly stable, at a very low level, but stable. So we need to do something else. And to do this, we split our simulation box in what we call buckets. These are radial tetrahedra. And we can sample various statistics in these little triangles at any radius we want. So we can plot things like the profiles of the tangential velocity close to the boundary, this is a small region around the boundary. You see that here we have convection, and then the tangential velocity drops, and you get to the stable stratification. So one way to define the convective boundary could be as the position where this decline is the steepest. Of course, for each of these buckets, you get a slightly different position. So this is one of the most important differences between 3D and 1D. This boundary has some fuzziness to it, or some uncertainty in this position. If we plot these positions as a function of time, then you have some initial transient due to this grid and the starting of convection. And then, well, the boundary goes slowly upwards, but there is a large spread in this. So this is a big difference. But one of the things that is clear, you could perhaps make some different decisions here and define this position in a slightly different way. But it's clear that the simulation box is being filled, or this convection zone is being filled by the fluid from the top. And the obvious question is how fast. You can integrate over the whole convection zone, and you get the amount of the entrained material as a function of time. And the growth of this curve is surprisingly very close to linear. You can do this at 768 cubed and also at 1536 cubed. And the slope of this curve is, of course, the entrainment rate. The difference between these two entrainment rates that we get at very different resolutions is only like 14%, which is quite encouraging. That usually things depend on resolution because there are processes that are unresolved. We get very similar results. What is even more interesting is that if you take this entrainment rate, and we know that there is about 0.2 solar masses in the stable layer between the oxygen shell and the carbon shell in the stellar model. So you divide 0.2 solar masses by this 10 to the minus 6 solar masses per second, and you get a time scale, which is about 2 days. So if convection really happens in this star in this way, at this rate, then these two shells could merge because the oxygen shell lives for 10 days, which is much more than this. So that these shells could merge and produce some nucleus synthesis, producing potassium and scandium, as I mentioned at the beginning. We didn't do this calculation yet, but this is just an estimate, and it leads to interesting things. I don't have that much time, but I'll go through this quickly, hopefully. So we have a series of simulations at 768 cubed, which the only difference between them is the luminosity of the heating source. And you get a very nice relation between the velocity of convection and the heating rate. The scaling is almost L to the 1/3, and there is a simple argument why it could be so. It's that the kinetic energy flux due to convection scales as rho v cubed, and the total flux scales as luminosity divided by r squared. But all of these convection zones have the same density and the same typical radius. So if you say that the kinetic energy flux is a constant fraction of the total flux, always, independently of the luminosity, then you get a scaling v proportional to L to the 1/3. And this is what we observe. If you take the entrainment rate as a function of luminosity, then you'll see that the entrainment rate is almost proportional to the luminosity. The exponent is 1.07. We don't have a simple explanation for this quite yet, but we can interpolate and extrapolate now. The luminosity of the actual star, although the stellar model, would be about here. So we really know what would be happening if we ran this at the nominal luminosity of the star. So the question now is, we have all this data, but what's usually implemented in star evolution codes is diffusion mixing. So how to translate our results into some form of effective diffusion coefficient or something that could be implemented in star evolution codes. Here I show the fractional volume of this lighter fluid in the convection zone at different times first there is no fluid in the convection zone, or no lighter fluid in the convection zone, and then it's being filled. So you can ask the question, what diffusion coefficient would be needed in the diffusion equation in order to produce this 1D behavior? You can calculate it easily, or relatively easily, and you get a profile like this. So this is the log of the diffusion coefficient, and you get this noisy curve here. Noisy because diffusion smooths everything out. And these profiles are flat here. So this is a poorly defined problem. But you get a very nice curve towards the boundary, and you see that as you get closer and closer to the top convective boundary, the diffusion coefficient really, really drops. This is the formal top of the convection zone. The mixing length theory, on the other hand, predicts this curve. So you see that there is a big difference. If you want to get this shape, then instead of the mixing length in the prescription for the diffusion coefficient, you can take not a constant, but a minimum of what is usually taken and the distance to the convective boundary. So as you go closer to the boundary, you decrease the typical mixing length, which sort of makes sense physically. And then you get this curve. It's still too low, but at least it has this about the right shape. So this was also seen by Porter and Woodward in 2000 in very different simulations of convection. And they also suggested to use this prescription. Now, if we look closer at this boundary here, this is only a small fraction of the whole simulation box. The convection zone is 4 megameters deep. This is 7.6, so this is 0.4 megameters. This is 10% of the convection zone. This blue curve here is the mixing coefficient from the mixing length theory, and it drops at the boundary because the theory predicts no mixing beyond the boundary. Our inversion gives you this black curve here, and you see the diffusion coefficient scale goes from 10 to the 15 to 10 to the 7, so you can see 8 orders of magnitude here. So this drop is very rapid, and you can model it. Usually this is taken in a star evolution code. So some diffusion coefficient applied close to the boundary, and it decreases exponentially with the distance with some parameter FCMB. We can fit this curve, and then you get this thing, this dashed line. It's a bit too low because, of course, the mixing length theory doesn't predict the right absolute value, but again, we can fit the right shape, and we could try to experiment putting this curve into a star evolution code. Just for comparison, this curve has been shifted to this blue solid curve so that you can compare the shapes. Pretty similar. Yes, so
where exactly does most of this additional synthesis take place that you're referring to?
this potassium problem, this happens when you entrain material from the carbon shell itself. So once these two shells merge, then you take some material, which is carbon region, there's some magnesium, and I don't know what else. I don't know the exact nucleosynthesis pattern, but the main thing is that you take this material and bring it down to the bottom of the oxygen shell to 2.2 or so gigakelvins. Then there are some reactions which release protons, and these protons are quickly captured on other things, leading to potassium and scandium.
Well, it's just that when you're showing these concentrations here.
Yeah, so I wanted to mention this.
At large rate, it's just what was confusing me.
Yes, so this whole region is the convective boundary. And I should have mentioned this. You have only the lighter fluid here. Then you have some transition to low levels, like 10 to the minus 3, 10 to the minus 2.5. You can see that this convective motion is slow enough so that it doesn't have enough energy to go to such high levels. It's only scraping of the lowest part of the boundary.
So just the X62 and 130 are the seeds for the potassium synthesis.
Okay, so if this was some carbon or magnesium-rich material, that would be the case. But in our case, we still have a 0.2 solar masses of stable neon-rich material, and only then the carbon shall begin.
Right.
So we would have to wait a lot more until the oxygen shell gets to the carbon shell, and then you get entrainment of carbon, magnesium, and everything else.
Half an hour instead of 10 days.
Yes. Or
It'll extrapolate all the way up for 10 days.
Or I have this prediction here. Where is it? Here. If this is the real entrainment rate, then we will reach the carbon shell in about 2 days. We can run it for half an hour or an hour at most.
What I'm asking is what the X62 and 130 refer to? They don't refer to potassium and scandium. The concentration is
These
a large radius, which is not what you're making.
Yes, so these concentrations are the concentrations of one of the fluids. So we have only 2 fluids in our simulations. One is in the convection zone, and the other makes up the stable layer.
You're just using it as a passive tracer, though.
It's not passive,
Well, it's not.
because it has some realistic mean molecular weight. Its composition doesn't matter too much for the dynamics. So only the mean molecular weights of the 2 things matter.
Right. Well, it's passive in the sense of it's got a different molecular weight.
Yes.
You're transporting it down to the bottom. Well, do you actually follow it all the way down to the bottom?
Yes.
Extend this far?
Yes, so these curves represent the material that you can see here as this blue and yellow stuff.
Right.
So all that you see here is only 10 to the minus 3 or so
Yeah.
by volume of the convection zone. All the rest is the original
It's
fluid.
just a scoop of a way of grabbing stuff outside of it. So take it all the way back down to the bottom, and then you make these 2 elements at the bottom.
Yes.
I'm just asking what this 62 and 130 refer to. That's all.
Yes, so they are referring to the fluid that was here in the initial condition. Yes. So that is the main problem. How quickly you can entrain this material, which is very buoyant because it has a lower mean molecular weight, into the convection zone. So if you do this fit, then you derive that the slope of the curve corresponds to a coefficient of 0.025. Now, of course, once we publish this, all the star evolution people will use this value for all of their convection zones. This is not what we need. This is what we get in our simulations of this particular oxygen shell. We still don't have any dependencies on the luminosity, for example. We still want to do this. And of course, this wouldn't be true, for example, for the bottom of the solar convection zone. So you really have to think about what you want to run in your solar evolution code and where to take this FCMB from. So this is something for the O shell.
Robert,
Yes.
do you have any physical intuition what would affect that value? So you did say you didn't actually test luminosity and so on, but
So most likely, if we go to higher luminosities, this F value would be higher. So that would correspond to, if you put a higher number here, a larger number here, then this decrease would be slower. So you would get larger diffusion coefficients at the same distance from the boundary. So that means that the entrainment rate, also in the evolution code, would be faster. Because if we do our simulations, then the entrainment rate goes up almost linearly with the luminosity. So this has to be somehow reflected in that coefficient. Of course, it's not only this coefficient that determines the mixing rate, because you also have this D0, so the diffusivity at the boundary, which depends on the convective velocity, which also goes up as you increase the luminosity. So we really need to.
That one you've got under control, you've got the scheme.
Sorry?
For that one, you've got the scaling of luminosity from your simple logarithm.
Yes, yes. That was done for the lowest of our luminosities, because here we have two simulations, actually, 768 cubed and 1536 cubed, and you can see that they are on top of each other. So you could say that they are sort of converged. And I could have mentioned this. There is another oxygen shell convection paper, Mikin and Arnett 2007, and some of the properties of their convective shell are very similar to our convective shells, and also the results are like this. Here the velocity is just a bit lower than what we predict. The entrainment rate is very similar if you take it as a function of luminosity, but not if you take it as a function of convective velocity. So the velocity field is somehow different in their simulation, and also the entrainment process is a bit different in their simulation.
What kind of resolution do they have?
I think their resolution is similar, but the issue is that they have a wedge, a 30-degree wedge. That means that the largest motions, or the largest modes in the convection zone are constrained. And we already see in our simulation that entrainment happens at places where you have two large-scale convective cells, and they converge, and then they drag the material to the bottom. If you constrain the largest scale, then of course there will be more of these smaller things, and you may get the same entrainment rate at lower velocity. So, well, that's our hypothesis for now. So to summarize my talk, I said that an important point from this research is that the boundary of a 3D convection zone is a finite thickness. So it's not a discontinuity, and you really have to think about how you really want to translate 3D simulations to 1D. There is not a single convective boundary. We got very similar entrainment rates at two very different resolutions, which is great. Our simulations suggest that a carbon-oxygen shell merger will be possible. We still want to test it in 1D with the effective diffusion coefficient, but we are already doing some experiments in which we replace the lighter fluid in our simulation with something that would contain some carbon, and we would burn that carbon once it has been entrained and brought to the bottom of the oxygen shell. We'll see what happens in the code. I showed you some nice scalings, and there are still open questions. Like, I showed you the diffusion model, but it's not the only thing that we could try. We know that convection is not a diffusive process, it's an advective process. So perhaps we could come up with a better 1D model that would match the properties of convection better. For something based on advection, maybe some up and down flow schemes, who knows. And of course, we still want to see what happens if we plug this 3D informed 1D mixing model into perhaps simplified stellar evolution code, and we run it for a longer period of time. For example, for the whole lifetime of the oxygen shell or some other shell. And we will want to compare what happens on longer time scales. Yeah, so that's about it. Thank you. If you have any questions, I'll be happy to answer them. Of course, there have already been some questions.
I have a very simple question there, we'll invest for that, but what would be the time scale for the kind of two shells that are separate and boundary in this case to become indistinguishable just because you haven't trained so much material?
Oh, so you mean when the two shells meet or start merging, you are interested in the time scale of this whole process?
Yeah, basically, you have just trained so much material that you don't have a preference for diffusion.
Yes, so then there's a big difference because you are two convection zones next to each other. They have slightly different mean molecular weights. It depends on what the entropy difference between them is. If it's small, then it will just overturn quickly.
I was just trying to make sure that, for example, stratification of your star like, within its lifetime?
We haven't tried doing two convection zone simulations yet, because the problem with the carbon shell is that it extends all the way to 60 megameters. Our simulations end at 8 megameters or 10 megameters. So the range of scales is just too big to do simulations of both at the same time. The simulations that I mentioned with carbon ingestion were a bit artificial in the sense that we put some carbon into a stable layer on top of the convection zone. So it's not the same thing. But I would expect that if you have two convection zones, then they would merge quite quickly once they touch.
One question. What is the prospect for using other computational methods going forward? So BPM isn't necessarily necessary, right, if you're looking at incompressible or largely incompressible flows. So what about anelastic models?
Yeah, so anelastic models are widely used because, of course, they have their advantages. We are limited by the sound crossing time, which is, of course, a disadvantage. We run this at Mach numbers of 10 to the minus 2 or so, which is about the lowest Mach number that makes sense for an explicit scheme. I haven't tried this in an elastic code, but well, hopefully the result would be similar. It would be cheaper for significantly lower Mach numbers, but it's important to think about this in the way that we really need to resolve very small scales. So it's not just that you have an elastic approximation, but your advection scheme matters. It's very important to have an advection scheme with very low artificial or numerical diffusivity.
Are you able to resolve P modes in the convection zone or G modes at the boundaries?
So we do see internal gravity waves. They weren't that well visible in my movies, but if you really look at pictures close by, you can see these almost horizontal waves. I haven't done any period analysis on this data, so I don't know about P modes. So pressure waves at such a low Mach number wouldn't be too important.
Right, the sun is not like everyone.
Yes.
Here, you said 0.2.
Yes. 0.01 minus 2. There is a very strong dependence in sound generation or sound amplitude as a function of the Mach number. That is a very steep dependence.